The next thing that we want to deal with here in section 4.1 is starting our operations with complex numbers. So again, a little bit of review from our work in college algebra. When it comes to actually dealing with operations with complex numbers, it's pretty straightforward. If you already have two numbers that are in our standard form, then to add or subtract them, you simply combine the like terms. In this case, combine real with real and imaginary with imaginary. So you can see here our basic definition. The sum of two complex numbers, a plus bi plus c plus di, is a plus c plus b plus di. So again, it's just what you would do normally. If we also, in this case, think about our difference as just being, maybe think about it as -1 times the coefficients on the second complex number, you see it's just the same basic concept. A goes with C because they're both real parts, and B goes with D because they're both imaginary parts. So it's really, really straightforward. It's just real with real, imaginary with imaginary, and perform the operation as normal. Keep in mind that this won't apply when it comes time for things like multiplication, where they get a little bit more complex, but this is enough to just kind of ease us into the basics for sum and difference. There's a couple other things that you might not have noticed back from college algebra when it comes to complex numbers. Since we have these operations like addition and subtraction, we might wonder if there's properties that we have for real numbers that also extend to complex numbers. And the short answer is yes. Things like the commutative property and associative property are going to exist, but there's some more interesting ones as well. See, we have the concept of an additive identity in the real numbers. You can add 0 to anything and you get the same number back. So that actually extends to the complex number system as well. The additive identity for complex numbers is also 0. In this case, you can think about it as 0 plus 0i. You don't change the real part, you don't change the imaginary part. And the reason I say 0 plus 0i is because of this next piece. If we have an additive identity, that means we must also have an additive inverse. So for a complex number a plus bi, its additive inverse is the opposite. So it'll be the opposite of a, and then in this case, plus the opposite of bi. Or as they've written it here, you could call it negative a minus bi. I don't really like using negative and minus here because we don't actually know what the coefficients of a and b are, but that might just be an easier way to read it. The point being is that this is a number so that when it's added to a plus bi, we end up with 0 plus 0i. A way to show that inverses create our identities here. So just a nice little touch, and the other reason I like to highlight it is it really starts getting you thinking about how complex numbers are viewed. We're so used to, from convention, thinking about a number as a single thing. But think about plenty of times in which you dealt with numbers that were not single entities. Anytime we talk about graphs, we talk about ordered pairs. That's a representation using two quantities. Same idea here. A complex number is made up of two parts. So don't think of a plus bi as two things. Think of a plus bi as one thing, one complex number. I think including this idea of the additive inverse for a complex number kind of helps to drive that point home, that a complex number is one whole thing. Now what we're going to go ahead and do to kind of round out this particular lecture is look at some example problems just to kind of make sure that we feel okay. So we're going to take a series of different complex numbers and look at their sums and differences. So let's go ahead and move ourselves over to the notepad and get to work over there. So I'm going to give us a series of complex number operations, again just focusing on sums and differences for right now. Our first one, we're going to have 4 plus 7i plus 1 minus 6i. So again, just follow the rule. Real goes with real and imaginary goes with imaginary. So in this case, I'll be doing 4 and 1. 4 plus 1, because that's addition. And then I'm also going to be doing 7i and negative 6i. They're still being added together. Let's go ahead and throw some parentheses around these. Real parts here. We'll have the plus in the middle from standard form. That's where this is coming from. And then the imaginary parts. So this will be 7 plus negative 6. And then the other piece from standard form is that this will just have I. So this is using our basic definition, reals and imaginary coefficients. Reals are going to give us 5. 7 plus negative 6, so this will end up being just positive 1. And then we have plus from standard form, and I also from standard form. And this is our final answer. Just always make sure that you're writing your complex numbers in standard form in order to be considered correct. Next one for us to take a look at, we're looking at 1 plus 2i plus 3 minus 2i. So same as before, real parts 1 and 3. Imaginary coefficients 2 and negative 2. Bring in the standard form with I here and plus in the middle. And we'll do a little bit of simplification. 4 and 0. So this is 4 plus 0i. If you wanted to, you could just write this as 4. This is still considered a complex number. It just so happens to be a real number as well with no imaginary parts. All right, what's next? Well, let's shift gears a little bit. We're going to go ahead and add in some additional terms and add in difference at the same time. So our next one, we have 3i minus negative 2 plus 3i minus 2 plus 5i. So there are a couple different ways to handle this. We know ultimately that we want to go ahead and work with the real parts and the imaginary parts separately, but I also have multiple subtractions here. So I'm going to do something that I would do normally with arithmetic. When I have something where I'm subtracting multiple parts, I like to distribute that negative to both. So before I do anything else, I'm just going to rewrite this as 3i plus 2 minus 3i minus 2 minus 5i. So I'm just distributing this negative and this negative before worrying about what comes next. Now let's go ahead and grab our real parts. So that's 2 and negative 2. Since I've switched everything's signs here, it's not subtraction anymore. I'm just adding up the real parts. And then let's grab the imaginary parts. 3i, negative 3i, negative 5i. So 3i, well, let's just do 3 because we don't need the I. We're just dealing with the coefficient. Plus negative 3 plus negative 5. Bring in standard form by tacking I onto the imaginary part, putting plus in between. So this will give us 0 for the real. On the imaginary side of things is going to give us negative 5. So this is going to be 0 plus negative 5i. Or again, if you prefer, you can just call this negative 5i. So this is a pure imaginary number in this case. One more example. Here we have 3 plus 2i plus 4 minus I minus 7 plus I. Same thing as before. I'm going to go ahead and distribute this negative to both parts so I can focus on just addition of reals with imaginaries. So this is 3 plus 2i. I can drop the parentheses as well. Plus 4 minus I minus 7 minus I. Reals 3, 4, negative 7. So 3 plus 4 plus negative 7. Imaginaries 2, negative 1, negative 1. So 2 plus negative 1 plus negative 1. And standard form plus and I. Well, interestingly enough, this will give me 0. And this will give me 0. So this ends up being 0 plus 0i. Or, if you want, just plain 0. In this particular case, we're not dealing with additive inverses here because we actually have 3 different complex numbers being combined. We could talk a little bit about how they play off of each other, but that'll be in a little bit of a later lecture. Keep this problem in mind because I'm going to bring it back as part of a later video to kind of show off some other ideas when we switch into the trigonometric plane. The last thing that I'm going to kind of mention here before we close out this video, you can see it for yourself on the last slide of the lecture notes. A lot of the properties for real numbers are also valid for complex. I've already mentioned commutative and associative, but also included that on that list are the distributive property of multiplication over addition as well as subtraction. So all of those properties are going to get carried forward as well. That last one, distributive property, is going to become relevant when we come back and we start looking at how do we take products of complex numbers in the next lecture.